Thank you. So welcome, I'm Caroline Champley. I'm the publisher of the new open access journal ePrime here at Elsevier, based in the UK. And I'm here with Karinesh Kant, who's one of our early career editorial board members. And we're excited to welcome you today to the third webinar in the series. Elsevier's ePrime was launched at the end of 2021. It's a new open access fast turnaround journal in electrical engineering, electronics and energy, and launched to help increase the impact of your research across disciplines. So today our webinar speaker is Professor Yuying Yan, and he will be presenting on smart methods of heat transfer enhancements. Yuying's paper on this subject is the most downloaded paper in ePrime. And if you have questions, then please ask them at any time in the chat. There'll be time for them at the end. And as you heard, the webinar is being recorded. And before I hand over to Yuying, I just wanted to quickly introduce him. Professor Yuying Yan is at Nottingham University, also here in the UK, and he's a chair professor in thermal fluids engineering. Yuying is a member of the UK National Heat Transfer Committee, and he's also a member of the EPSRC Peer Review College, a fellow of ISBE, that's the International Society of Bionic Engineering. Yuying has chaired or co-chaired more than 10 international events and conferences. He's also the recipient of several awards. Professor Yuying Yan has supervised more than 40 PhD students so far, and he's been the author or co-author of over 450 papers, many of which, more than 300, are in journal papers. So Yuying is also a senior editor for ePrime, associate editor for Elsevier's case studies in thermal engineering. And he's a board member of journals in heat and mass transfer, bionic engineering, energy storage and savings, as well as automotive innovation. So really looking forward to hearing your presentation today, Yuying. So without further ado, I'll hand over to you. Thank you very much for joining us today.
Okay, thank you very much. And hello, everybody. And thanks for Karen's introduction and arrangement. And good morning, and good afternoon, good evening from all over the world and friends. So my topic today lecture is thermal management. I will talk about the state of the art. Now, first, I give the outline. The lecture will be divided into 4 parts. And first, I will introduce the background of the power electronic development, the impact to the society, and the relationship with thermal management. Then I will going to talk about the challenges of the thermal management. And after that, I will talk about how to tackle the challenge. And I will give an overview of the technology development and also the recent advances. Finally, the conclusion and outlook. Modern harmonious and sustainable society is a big topic, as they are concerned with many aspects, such as the policies and human relationship and technology development and so on. But from a science and technology point of view, they must have the following important functions, such as having easy and effective telecommunications, networks and systems, nowadays online banking, shopping, social media, etc. The energy supply and utilization must be effective, green, renewable, and sustainable. Also, electrification, including modern transportations, media, medical equipment, and so on, and should be well in place and adapted. So what are behind this is power electronics and semiconductor integrated circuit. In terms of telecommunications and effectiveness, durability, safety of the system and the network and data center has become extremely important nowadays. It's a part of the harmonious and the sustainable society. Also, we can't afford the system freely. And since the COVID-19 pandemic, particularly, more often people need to work from home. We need to virtual lectures, virtual conference, online shopping, etc. Electrification are important parts of a modern harmonious society. The most notable progress in 21st century probably is the development of electric vehicle. It is predicted by 2030, the global market will be over 39 million units, compared with just over 8 million nowadays. The electric car is an electric unit, including the high-speed e-motor, power module, power batteries, mainly the Li-ion batteries. The development alternative, the development of autonomous vehicle and flight vehicles also largely rely on power electronics and artificial intelligence to control the semiconductor product. So other vehicles like high-speed railways are also more related to power electronic semiconductors. Modern clean renewable energy, such as the wind farm, solar farm, tide energy generations, and their combination are also the important part of harmonious and sustainable society. And an important component in such energy system is IGBT, which is the three-terminal power semiconductor devices. IGBT has been widely employed in renewable energy applications and also electric cars and high-speed railways. Currently, the chips can only dissipate no more than 10 kilowatts of power. The heat flux of IGBT used in hybrid electric vehicle is now at a level 100 to 150 watt per square centimeters during the normal situation. However, with the increase in the capacity of electric current and the switching frequency, the heat flux at 500 watt per square centimeters or even higher could be certainly will be expected. So when we talk about electronic development and the thermal management, we have to briefly review the history of electronic development. Since Jacobi introduced the early concept in 1949, the integrated circuit has been developed rapidly. The integrated circuit is usually the small chip made of semiconductor material, silicon, manufactured by even several nanometer process, and could accommodate millions or billions of microstructures such as transistor, resistor, and capacitors. 2019, one chip can accommodate 3.5 billion transistors, but nowadays that figure will be even higher. The integrated circuit has been used in almost all electronic devices. The modern life has also been integrated with various electronic products very deeply. Over the last 70 years, application of semiconductors and electronic products have significantly improved the quality and the efficiency of the modern people's work and life. The product has much influence to work toward modern societies. The four stages could be covered applications of the integrated circuit. So we can see this is for industry and for medicine, for home use, and for else that's including the shopping, banking, and so on. In terms of the faster development of integrated circuits, the famous Moore law must be mentioned, which is proposed in 1960s. Although Moore's law is essentially like empirical relations in production rather than the natural law, its accuracy has been proved for decades, and the law has been widely used to guide research and development goal in the semiconductor industry. Based on Moore's law, the number of transistors you can see, and that can be accommodated on the integrated circuit will keep increase exponentially. Simultaneously, the increase in demand in current electronic devices move forward with resistation, thinness, and lightness. So obviously more transistors and the small size and devices also means the more power consumptions and higher heat flux density. So to know, and the heat flux density of advanced server equipment chip can reach to 1 megawatt per square centimeters. And the heat flux density of some equipment, like the phased array radar, that can even reach 5 to 10 megawatt per square centimeters. As a result, in order to maintain the safety operation, the thermal management faces greater challenges. Based on the data 2013, approximately 55% of electronic equipment failure was due to the high temperature or high heat concentration. This figure has increased to 65 to 80% in 2022 last year. So certainly we need to do something to improve thermal management. What is thermal management? In fact, it is often an integrated solution to tackle the thermal challenges. So first, let's have a look at the global problem. One of the problems is too hot. The Earth's temperature becomes too high. But in the UK and many other countries, people experience the hottest summer in 2022. And this could be resulting in many problems. So what is the solution? Government leaders, that is, we need thermal management. The government leaders and have had global summit COP26, 27 to find and work out solutions of thermal management for Earth, try to let the temperature down or rise slowly. Another global problem is COVID. Too many people have a high temperature. Once upon a time, measuring body temperature become popular, and the people need thermal management, obviously. Action seems to be the vaccination path, using medicine such as paracetamol to maintain the normal body temperatures. Now look at the power electronics. Mobile phone is obviously a good example. Phone has become smart, more efficient, but more power consumption. The heat flux density increased almost exponentially, but decrease the thickness is also continuously demanded. The other example is data centers. It is predicted nowadays, from a global point of view, the energy consumption from cooling is much higher than the consumption from heating. And this is probably true, as there's millions of data centers working around the world. But the question remains, is the data center thermal management sufficient or efficient? Obviously, conventional method using air conditioning cannot do the job properly. It needs more effective and accurate cooling. But we need to know where is the hot, where is the hot spot, and where is to be cooled. Also, similarly, electric car battery safety could also be the example. Overheated battery will result in a fire explosion. So we understand without a proper thermal management, obviously landing on Moon or Mars will be impossible. How to effectively do thermal management? We can learn this from human thermal management. Human beings are expert for thermal management. Human body temperature are controlled perfectly at about 36.5 to 37 degrees C, which is always crucial. To keep warm, either passively by clothing or actively by enhance, the heat exchange. In this case of the illness, body temperature may be increased to the level higher than the safety temperature, but it can be normally be treated down by either physically or chemically, similar to human. Plant and like a flower and vegetables also need proper thermal management. This is that we can always learn a lot from nature. How to take the challenge of increased demand of thermal management. For electronics, the state of art has been reviewed by a recent paper. So I'm going to talk of this firstly, and draw your attention about accurate cooling. Sometimes we need to more accurate thermal management. One interesting example is hyperthermia treatment for cancer. It could be an alternative cancer therapy by external controlling temperature of a cancer cell. Cancer has become and still be one of the top killers for human life. But we have learned cancer cell cannot be live when the temperature rises to above 42 to 46 degrees C. Although human cannot afford such a high temperature, but locally, the higher may not be damaged life. And the technology enables doctors to raise the tumor local temperature to such a high level. So through the induction of heating of implant the magnetic nanoparticle by alternative current magnetic field. So magnetic field will increase the anisotropy of the nanoparticle cluster to increase in the internal energy, such as the temperature. So this example indicates the importance of accurate thermal management. So some electronic and equipment obviously also need more accurate thermal management. For instance, the chips in IGBT, the supercomputer, data center servers, and the electric car motors. There now is currently available technology of thermal management. Can this technology have tackled the challenge? So in general, this could be divided into two categories, namely direct cooling or indirect cooling. Direct cooling includes air cooling, immersion cooling, and cooling by drop electrowetting, and spin cooling and jet impingement. So we will explore each of them respectively. The easiest way to achieve electronic thermal management is natural convection cooling. And because this is the economic and convenient method. But nowadays, actually this report is still quite limited because of natural convection basically is a mature technology and mainly for low power electronics. It is recommended the radiation and the free convection are only recommended for heat dissipation for lower than 1,550 watt per square meters heat flux density. For higher power electronic device, forced air or liquid cooling is more reliable. Immersion cooling is an effective thermal management. It uses dielectric fluid or coolant with good thermal conductivity and very poor electrical conductivity property. Immersing the electronic devices to achieve cooling. So the application of immersion cooling could include data centers, charge stations, also could be for electric car battery and car power electronics. Immersion cooling can effectively cool electronic devices, but some issues need to be handled. Fluff floating in the coolant could be adsorbed on the heat exchange surface. And the balance between the electric insulation and the thermal conductivity of coolant is also important for immersion cooling. Further research also need to address like the aging of the electronic devices with the various coolant. Commonly, and use the coolant now available in the market, as will be listed in the table. So technology over here cooling is electrical whiting, which is an effective method to control the droplet whiting. Electrowhiting is an electrocapillary phenomenon. The surface charge generated at the solid-liquid interface by external voltage improves the availability. Electrocapillary is the first proposed by Dunbury-Liebman in 1875 as an electrocapillary phenomenon. Nowadays, the droplet electrowhiting has many applications in thermal management of electronic devices. The representative technology for droplet electrowhiting is so-called electrowhiting on dielectric. It's called the EWOD, which has advantages of quick response, hot spot cooling, and low energy consumption, because there's a low pressure drop. The mechanism for drop from a stationary to move based on the EWOD, the characteristics and the polarization theory has been intensively studied. In the present, this method has major applications to digital microfluidics, which is widely regarded as an elegant technology to reduce the reagent and energy consumption. This is very important. We mentioned about spin cooling. It is probably one of the most effective thermal management technology for high power electronic devices. Due to its capability for high heat flux dissipation and a sizable and cooling area, it uses a nozzle to break down the cooling fluid into numerous tiny droplets by high pressure. Then the droplets impact directly on the heated surface and to achieve the effect of enhancing heat transfer. The placement and structure of the nozzle have a critical influence on heat transfer performance. Pressure and the subcooling degree also make the impact. Spin cooling process can be divided into the typical 3 stages at different wall temperatures, as a single phase stage and the 2-phase regime, and also after reaching the critical heat flux. It is reported passive spin cooling could be increased specific heat flux compared with the continuous spin cooling. So this is the PIV could be used to observe the velocity distribution of autonomous droplets by different nozzle pole size. The report is heat transfer performance will be increased with the nozzle pole size, making Tom's droplet velocity lower but even distributed. It's also increased with the surface coverage area. The physical properties of a heating surface also have a significant effect on cooling performance. Many researchers had studied about the surface roughness and how this could be improved the spin cooling performance. Microstructures and nanoporous flight surface are prepared and investigated in a number of studies. Both advantages and disadvantages of spin cooling can be identified. It is an effective solution for thermal management for high power electronic device. Nozzle structure and position and fluid property could affect the cooling performance. However, in terms of the disadvantages, they need high pressure operating conditions, and closing of the nozzle during the practical operation may occur. But overall, the heat and mass transfer mechanism of spin or film nuclear boiling is still sort of intensive investigation. Now we'll have a look at the challenges of automotive thermal management. Here I use our recent project for ACE Drive, sponsored by the Innovate UK as an example. ACE Drive is one of the biggest projects in recent years in the UK, and 8 million pounds sponsor aims to develop advanced cool and integration of electrification driving system, consisting of inverter, e-motor, and transmission gearbox. The e-motor and electrical engine is of high speed and high torque and high power density. But considering the overall heating and cooling load, motor cooling of 4 to 10 kilowatt, power module 2 to 6 kilowatt, and so we will really need an integrated solution of thinking. What's the challenge target? Is the electrical engine or motor. The peak power of the target motor is 140 kilowatt at least 30 seconds. And the maximum motor speed is up to 21,000 APM or even higher. Well, the heat loss of the motor is expected over 10 kilowatt, and most of the heat is generated in winding. In terms of thermal controlling, the temperature of all components in the motor must be below 220 degrees C. Here's the basic concept of the electric motor thermal management. In general, most of the heat loss from motor are from winding, including slot winding and also the unwinding. The motor is a very complicated thermal system with different components preferring the different temperature level. Obviously, both heat transfer performance and the electromagnetic influence should be considered in the thermal management for the motor. The conventional water jacket cooling, that is probably not enough for effective thermal management, or we need a more accurate cooling, that is direct cooling from to the winding. Therefore, thermal management for e-motor has become more complex. The advanced cooling method, including force convection, jet impingement, and spin cooling, should be considered. In terms of heat transfer against the motor, the electric current, density of torque, there are 4 stages of complexity of thermal management could be identified. The e-motor or modern electrical car are in the 3rd or 4th stages of thermal management. Obviously, the better, more efficient solution are required. But some solution maybe also means more complex and costly. This shows some recent results of e-motor spin cooling. On the environmental side, the spin parameter and the flow rate, pressure, temperature, and the nozzle layout were studied and optimized. The effective oil flow rate and the temperature gradient of the slot winding with a different oil temperature is studied, and the effect of oil flow on the motor teeth and the temperature gradient is also obtained. On the model development, the long parameter model and the CFD model, both for motor and the spin process, has been developed. On demo test, the demo motor was manufactured and the temperature was within safety range with new technology and design. So now we talk about the jet impingement cooling. Similar to spin cooling, jet impingement is an effective cooling method with a relatively low thermal resistance. It has widely been employed as a thermal management solution. Air or liquid jet impingement region shown here. So this technology has already been well applied to the turbo machinery industry, like turbo blade cooling. The jet impingement cooling process is similar to spin cooling, but it doesn't need drop atomization. So nevertheless, the fluid flow and heat transfer mechanism is still very complicated. It is reported the multi-jet cooling could be more effective than the single jet cooling. Relevant experiment study and the result has been reported in quite a few publications. So now we move to indirect cooling. So which means the cooling media dissipate heat combined by the external heat sink structure. So first, it was mentioned about air gap between the electric device and the heat sink surface. this very significant impact on the heat removal process. So therefore, the thermal interface material called TIM should be accepted. The thermal conductivity of TIM can be improved. The current is low, so that improvement could be like adding nanoparticles using carbon nanotubes and so on. Indirect cooling technology could be included microchannel cooling, thermal electric cooling, phase change material method, and heat pipe and vapor chambers. Microchannel heating method has been applied for many years now. It is initially proposed in 1981 by the and trees. The size of a microchannel could be as small as 1 to 100 micrometers or 10 to 100 micrometers. And such microchannel heat sink has a strong capability of heat dissipation because large surface area could reach more than 1,000 watts per square centimeters and a better temperature uniformity. And typical microchannel heat sink has been applied to the thermal management of electronic or semiconductor chips. The study of heat transfer in microchannel is one of the hottest topics. So we can see over the past 30 years, the number of publications, and that is publications with the name of a microchannel over the last 10 years has been significant increase. Major research focused on microchannel heat, including the structural design, such as the change of structural parameters, and also the improvement of channel structures and the properties like mobility, wettability. Also, including the design like a double layer microchannel, manifold layout. And the design of manifold is very important. And it can better guide the layout of flow channel and realize the balance of flow resistance reduction and heat transfer enhancement. Many microchannel structures have been applied to the optimization for microchannels. This include like dipole and the protrusion surface and the pinfin surface, rib, groove, cavities, vortex generator, interrupter wall, and the metal forms. So largely, this has been applied to microchannel, but the fabrication is still very challenging. Overall, microchannel cooling has been proved to be very effective thermal management method for high-power electron device. It is a great deal of research has been carried out, but fabrication of microchannel is still plagued by machine accuracy, manufacturing cost, and the process simplicity. The fabrication method of microchannel also need improvement. The critical parameter for microchannel heat sink, such as the material size, flow channel layout, and microstructural placement, and also general method of optimization design need to be further explored. Although nanofluids applied to microchannel could help to improve heat transfer, but some research claim after a certain period of the working, the deposition and the nanoparticle will be a problem. So the issue is there. But they worry about the possible closing of microchannel, making it inefficient and resulting overheating and damage the devices. So it has to be considered. Flue boiling is certainly an effective way for enhancing heat transfer, but also feasible method for reducing the flow resistance and suppressing two-phase instability, and also for further investigation. So some solutions inspired from nature could have to improve heat transfer surface morphology and wettability. As we know, the various objects, like from nature, such as a plant, bacterial, insects, and aquatic animal, and the bird, all that have selective functions. Some functions are very useful and helpful. For example, the typical function of plant boundary layer on hydrophobic microstructural surface can be identified, such as the surface wettability, anti-adhesion, self-cleaning properties, and the surface temperatures. Surface superhydrophobicity with a self-cleaning or adhesion property can be found from typical plant leaf boundaries, such as the lotus leaf and the rosa petals. Based on the modeling and observation of nature objects, it is widely understood that the hierarchical surface structure is needed to develop the composite interface with high stability. So this will be greatly helpful for fabrications of heat transfer surface and microchannels and for electronic cooling. When we talk about heat pipe cooling. In fact, the heat pipe is not just for cooling. It is widely regarded as a super thermal conductor because it's a very high equivalent thermal conductivity. It often played a role in maintaining the isothermality. So this could be simply solved by a comparison about if you transfer 200 watt heat through copper tube or heat pipe, you can see the temperature difference. One is 70 degrees C, one is 0.5 degrees C. So you can see what is the super thermal conductivity. A heat pipe is a heat transfer device that employs the phase change of evaporation and condensation to transfer heat between the two solid interface. The difference between heat pipe and the thermal siphon tube is the introduction of the weak structural material or enabled heat pipe work in any orientations. In fact, over the last 30 or 40 years, major development of heat pipe technology is the weak structural innovation. This enabled the scientists and engineers to develop ultra-thin heat pipe and flexible heat pipe. This is for electronic devices, cooling, and thermal management. So I listed a few, reference for this contribution. That lead author, Dr. Yuying Yan, is our former Marie Curie Fellow, now is a professor at South China University of Technology. Due to its simple structure, high reliability, and efficient heat transfer capacity, heat pipe can be applied to thermal management of high-power electronic devices, including the electric car and the battery. So our test result has been published in 2015. Heat pipe can also be applied to data center cooling for more accurate thermal management. Conventional way of indirect cooling, such as using air conditioning or air cool, is insufficient. By introducing heat pipe, you can see it is by introducing heat pipe, the cooling can be more efficient. Heat removal could be more accurate and straightforward. So this is an example of application of combining heat pipe and the water cooling system for data center cooling and thermal management. The principle is using heat pipe to accurately position under the hotspot, and heat pipe almost isothermally deliver heat to water channel heat changes. Another type of heat pipe is, we say the vapor chamber. Vapor chamber is a heat dissipation structure. As a heat structure can be used for thermal management of electronic devices. Vapor chamber has advantages of favorable temperature uniformity, suitable for devices for heat flux and a large surface area, and high reliability. As a basic structure and the working principle similar to heat pipe, so it's called a flex pipe. So in recent study, micro pillars are combined with a copper mesh weak structure to normal ultra thin vapor structure. as shown in the figure. The results show that this kind of ultra-thin vapor chamber can have 30 times higher thermal conductivity than pure copper. And the change of maximum heat transfer performance is less than 11% under real gravity. So this is an example for vapor chamber applied to integrated circuit packaging. And the structure of IGBT is by comparing the traditional indirect cooling and direct cooling attached with copper-based IGBT model, and the indirect cooling attached with vapor chamber-based plate. The heat transfer coefficient compared with the heat input is compared for the vapor chamber-based plate heat sink with the copper-based heat plate heat sink. The result also show that the heat transfer coefficient for vapor chamber base plate heat sink is much higher than for that with the copper base plate heat sink, especially for the high heat flux. So this is a part of our work and completed years ago. Is sponsored by the Innovate UK project. Is collaborated with Denmark. Function of heat pipe, or the heat transfer performance of heat pipe or vapor chambers are still on the way to be improved. Basically, we try to overcome some major limitations, such as viscosity limit, Sony limit, trample, capillary limit, and boiling limit. Obviously, this is a very difficult challenge. Again, something we can learn from nature. Nature may help to give us useful solutions. With regarding the improved capillary limit, the function of liquid migration from the roots to leaf of the plant, such as the banana trees, cactus, have been studied in our laboratory. MRI, magnetic resonance imaging technology, is important to have investigate and understand the mechanism. Although this is just a few tests, some progress has been obtained. Now we move to thermoelectric. Thermoelectric cooling, that is, we have to mention, but Thomas feedback from that is 1821 could use the temperature difference to realize the conversion of thermal to electricity. That's called the feedback effect. After that, 1834, Petty discovered the thermal electrical model can be transfer heat, and based on this, the effect is named. Petty effect means the temperature difference can be produced through the electrical current flow between the two electrical connection points. Major application of TE cooling on Petty effect can be identified mainly is for the LED cooling, electronic cooling, TE heat pump, and the TE refrigerators. So one of the recent applications in all of them is the TE cooling is to the energy harvesting of automotive. The effective use energy from car exhaust gas are device called functional exhaust pipe is designed. TE is the model for energy conversion. The exhaust or waste heat to electricity convert, and based on the feedback effect. And heat pipe adapted to TE model to have transfer heat from exhaust gas to TE, also from TE to cooling. As a result, the waste heat from exhaust gas be used to convert to electricity, the high power energy. So overall thermal efficiency of the car engine is largely improved. Finally, talk about the phase change material application for cooling. Phase change is a series of substance and can absorb or release heat, latent heat through the phase change process. As a medium of heat absorption and storage and release, the characteristic PCM have a significant effect on cooling capacity. So Whereas the PCM based on heatsink has been designed and developed. In terms of applications, the following feature has been summarized. Like a PCM is usually combined with various kind of heatsink to maximum their advantages. The pin-thin heatsink is the most, versatile amount of them, and the common say the pin-thin and is a directive structure combined PCM. The most of PCM have a relatively low thermal conductivity, and to enhance heat transfer, metal form could be applied. Some scanning magnetic microscope image can indicate and the metallic form structure, and also the numerical modeling work has been well presented and developed over the last few years. Recent effort has been focused on improved PCM applications for high temperature thermal management, such as applied to the solar farm with a solar salt, like 60% of sodium nitrate and 40% of potassium nitrate as a PCM, and the silicon carbon ceramic as a porous mesh to improve the property against the corrosion. So nature inspect solution has been explored and to effectiveness of shape establish the PCM and to enhance heat transfer. Nanofluid are suspension of nanoparticles in the basic fluid and has been easily to be obtained nowadays, could be prepared. And we just mentioned about, although there are issues in terms of application in flow boiling, no phase change applications to electronic cooling or thermal management are still attractive. Some progress has been made over the past few years. You can see our publications and also the applications of a nano-encapsulated phase change material to heat transfer and to energy storage, and also possibly for pulsated heat pipe could be very attractive. Now I would like to draw a conclusion and outlook. And both technology of direct cooling and the indirect cooling have played an important role in thermal management of electronic equipment or devices. The improvement of structural designs will still play an essential role in thermal management. Thermal conductivity of materials used in heatsink, heat spray, and thermal interface materials is crucial to thermal management. For both direct cooling and indirect cooling, surface properties such as wettability and roughness can significantly affect the flow and heat transfer. Nature may have to offer useful solutions. Nanotechnology, including nanoparticles, nanomicro encapsulated PCM used for electronic cooling, should be further explored. Although phase change process enhance heat transfer effectively for high power electronic device thermal management, effective liquid cooling, liquid direct cooling, including immersion cooling and liquid direct cooling, are still a good option for many future applications. So I would like to acknowledge my co-authors and PhD student Hao Zhang and Xiu Hui Wang, who is the co-author for the review paper, and also a few of our publications I have mentioned in this. Thank you very much for your attention.
Hello, Professor. Hello, Professor Anand. Thank you for such a nice presentation. Now I would like to invite participants to ask questions. Does anyone have a question? Hey, if you want, you can ask a question.
Oh, hi, Karen. So I had a question. I was just wondering
Yeah.
about the. I was interested to hear Professor explain where there will be continued development, and I wondered if, and that would be in the area of nanotech. I wondered if there any other up and coming hot topics. So perhaps given the situation with energy storage, I don't know whether there are other hot topics that you foresee coming up, Professor Yang.
Yes. Yes, I think for energy, because like E prime, that is electrical, electronic, and energy. Energy has many topics related to thermal management, and typically like energy storage. Energy storage is become increasingly important and draw increased attention from the community, for the government, for the companies, because we know, but that could be improved overall efficiency, not only for energy utilization, but also I think for electronics, that is also very important.
Thank you. Thanks for that.
Okay, thank you. The next question is, what is the maximum heat that can be removed using the Peltier devices?
I think using the thermoelectric, and that's a good question. I think currently, and the thermoelectric is still under intensive investigation, and it depends on the, that is the current application, as far as I know, is a very small temperature difference. We try to use inside inventors called the TE heat pump. That the temperature difference is very small, but there are many small temperature difference applications in electronic, like the sensors and the probably. But the problem I think is about the currently the material and the semiconductor material and used for the TE. And because some application need a relatively flexible material application.
Okay, thank you. Thank you. The next question is from Gan from KIT. So he's asking your opinion on the future of thermal management in solar energy applications.
Yeah, thanks for. I think for solar energy application, that is a move to another scenarios for relatively high temperature application. But currently the PCM, for example, apply for the is a relatively low temperature, the phase change, but for solar farm, and we need a relatively high temperature. For example, at the side the sodium nitrate, that is the phase change, the temperature will be 600 degrees C, and so the thermal management is going to be more challenge. So we have a recent paper mentioned about the publishing nano energy, and we try to develop using the solar salt that's with a relatively high temperature, phase change temperature, but obviously they face the problem of corrosion. The corrosion, that means using metal form to enhance the thermal conductivity may not be a good choice because the corrosion happen. So we try to think about the ceramic. So that is a really challenging area.
Okay, so further question is, do you think it will be efficient to use Peltier devices for cooling high power semiconductor devices?
To my knowledge, to be honest, I don't think that is possible. I think Peltier device could be just for the small temperature difference application, the relatively low temperature.
Okay, thank you. So anyone further, any question?
Professor Yan, this is Yi. May I ask some question? And thank you for your presentation. And I have two questions. First, a question that we know we have new materials every day. For example, we have the silicon carbide, we have gallium nitride. Will in the future, the new generation semiconductor material will, because they can withstand a high temperature itself. So with the new generation material, will reduce the importance of the cooling management in the future or not? And could you give us some comments?
Yeah, I think that is a very good topic. Today, my talk is actually is based on our published review paper. It's just a review the recent applications, but not actually deeply explore in a particular technology. I think for the power electronic design, and it's really challenges. It depends on often have a very compact space, and also they need to think about heat need to remove the within the space, and so that is going to be very challenging. That is why we need, so for example, like a spin cooling, we need sometimes we need but sometimes the immersion or it depends on many factors. But immersion, it must be the dielectrical for very low, electric conduct. But that is because this is no turbulence or no phase change. That's the heat capacity they remove. That's limited. But some people believe is direct liquid cooling. For example, using liquid metal as a liquid direct cooling. So that could play the similar role as a phase change achieved. So it depends on the geometry and applications, I think.
Thank you. I probably have a second question that because you have done very interesting topics on the thermal management, the EV and battery. That is a very hot topic, and currently, could you share some comments or some perspective from you on this specific topic? And because you have a very good project.
Yeah, we have. I think for the battery thermal management, and we just take the example for electric car. I think that is still a very interesting topic nowadays. Many automotive, the engineer and the research, even the scientist, it's interesting topic because it's difficult to have for example, liquid cooling. The cooling method that is all available, but because the vehicle is a need to on the road, they have a vibration, they have they need to overcome different the severe circumstance, so they need a durability. We in 2015 we report and using heat pipe. That's a very good design. The heat pipe could be, because I say the battery like a human. They have an optimum operating temperature, like a 25 to 40 degrees C. We need to control temperature. It's not too high, not too low, because we need the highest temperature, like a human body. Okay, so many methods can do the job, but they were like we can't use water direct cooled battery, and we can't use in the microchannel. But you can use microchannel, but we need to think about the vibration and the discharge and many things. Heat pipe is very good, but they have increased the weight. The lightweightization is also the target for vehicle. Once we need the green, but also need to light. So that is sometimes is a class. It's difficult, but I think it depends on. But now I think it's available. Is the conventional is the cooling using the current. I think applied in the dominant in the market is still the liquid cooling.
Okay, thank you very much. Thank you for your answer.
Thank you, Professor. Anyone have a question? So, Further, no questions, Caroline?
If anyone did want
Yeah.
to verbally ask a question, you can raise your hand and we can unmute you. So I didn't realise you're unable to unmute yourselves. So do raise your hand if you wanted to ask a final question. I'm conscious we're at the end of the time. Okay. Well, thank you. Thank you so much, Professor Yuying, for your really interesting presentation today, and some great questions as well. Thanks everyone for joining. We'll be sharing the slides and the recording on the ePrime website. And yeah, don't hesitate to submit to the journal. And thank you very much, everyone, for your time. It's been a great presentation. Have a good day.
Thank you.
Bye. Thank you.
Bye. Thank you.
Bye.